future of the national subsea industry, standardization and modularization, the key to success. Edited by DRASS. This presentation aims to explore the various sectors that make up the subsea microcosm, initially through an overview of DRASS capabilities and products. But in addition to assessing the technical complexity of the sector, we will try to describe the immense potential for development and synergies that we have in front of us as the Italian system. This reflects the technological superiority that our industry can boast over international competition and that we want to maintain. By producing better performing basic components, a considerable advantage at the system level is gained. Every single object presented here is the result of studies and experiments. As an example, for underwater electrical connectors, we have introduced new resin technology, achieving much higher reliability and reducing the likelihood of low insulation. This means that our components increase the total reliability of complex systems. We have made breakthroughs in digital signal processing. We are the only ones to have developed multi-gas hyperbaric analyzers, meaning that once connected to any gas cell, they automatically become complex analyzers of that gas. This occupies less space and the need for spare parts on board. Let's move on to the breathing apparatus for extreme depths. Our new diving helmet, the D1, was unveiled to the oil and gas sector at Offshore Europe 2019 in Aberdeen. The D1 is a formidable innovation by current market standards because a single helmet supports 3 dive modes. Until now, 3 different helmets have been needed. Producing a breathing mask or helmet is no small achievement. Heavy investment is needed in testing and simulation equipment built to specification. DRASS has the most advanced laboratory for breathing devices at depth, and all of this created without government funding. Let's go back to the sea for a moment, because the development of DRASS components is aimed to support the integration of complex projects. We have designed diving boats with more compact dimensions and enhanced performance. This is thanks to the hyperbaric chamber installed on the keel that ensures better stability. We have also developed 2 rapid response submersible support and rescue vessels. The multifunctional coastal minehunter design is capable of embarking on modern autonomous systems, and it allows modular use of the same platform as a Special Forces support ship, diving ship, mine layer, and hydrographic vessel. Thanks to the cooperation with Carbon Dream, the conventional fiberglass is replaced by better performing advanced composite materials. But our greatest achievement to date is converting an offshore ship into the most modern submarine rescue vessel. What you see is the result of a consolidated experience in the offshore industry. DRASS has completed more diving vessels than all our global competitors combined in the last 15 years. This ship embeds complex and specialized systems. DRASS 100 series hyperbaric decompression chambers with automatic control represent a worldwide standard for offshore diving. The ship is equipped with a diving bell for deep dives from 300 meters deep and beyond. the remotely controlled submersible rescue vehicle, designed in cooperation with Saipem, will play a key role later in this presentation. Now let's get ready to dive in and explore the vehicles for the Special Forces. We will also take a closer look at the range of compact submarines, ranging from 85 to 450 tons, along with their associated weapon system by Leonardo. Here is a world that contains a microcosm of technology. Without itemizing the vehicles for Special Forces, let's focus on the Integrated Submarine Control System. A further development is the digital periscope that synthesizes infrared and optical data in cooperation with Flyby. Now let's focus on what happens under a submersible rescue ship, where different systems contribute to the mission. We can operate the Rapid Intervention Rescue Capsule, or release the divers with the diving bell we mentioned earlier. We can connect the ventilation system to supply fresh air to the sub. And finally, we can deploy the remote-guided submersible rescue vehicle seen above, which represents a steep technological evolution compared to current piloted vehicles. Aside from the graphic simplifications, you can see that it's a little crowded down there, and that's going to be the guiding topic from now on. In the local domain, the concept we are working on with engineering is an air traffic control solution applied to diving. The goal is to map the location and motion parameters of the underwater assets for coordinated and safe operation of multiple vehicles during a rescue mission. Now let's broaden the view. It is a common opinion that the future will see an expansion of crafts and traffic, given the strategic value of the sea in terms of food and mineral resources and the importance of maritime routes. Of course, there is also a need to keep all of this safe. The control of the seas in the future will be as important as the control of the sky has been until now. It will take place through a wide network of dual-use sensors, carriers and payloads, mainly resident on the seabed. Being in control of the subsea environment means being able to manage this network and interface its components. As we get even closer, we see individual objects that now exist and are in the process of being developed, as you will see later in this presentation. Here you see ROVs, unmanned sonar vehicles, and sonar and subsea charging stations, technology already existing in our industry. Subsea, you find sensors placed on the seabed and processing information as you would find with a network of space satellites. You see charging stations for the recharging of resident vectors that carry their cargo either autonomously or wire-guided. The payload represents the specific asset which is deployed to perform the assigned missions. Such a network will transport the highest variety of payload for defence and civilian applications. The complexity of managing the system on a global level therefore requires the identification of methods that ensure interoperability. The DRASS Modular Submarine Rescue System is designed with an architecture which is tailored to indicate a possible approach. A carrier is any object capable of performing transportation at surface level or above. It can be a ship, a surfacing submarine, or even an aircraft equipped with launch and recovery systems. A vector instead carries the payload subsea, and in general the distinction will be between autonomous and wire-guided vehicles. The payload in this case is a submersible rescue capsule but can also be a set of autonomous vehicles or an array of passive sonars, or even a microplastic sampling system or a pollution detection device. All of these connect with the same interface to the vector. Using as an example the interface between vector and payload, we can see that it is like a giant USB cable of the abyss, which serves to connect every device. The interface must ensure mechanical standards to connect objects of increasing weight and dimension, cater for different electrical voltage, and support subsea communication systems depending on the distance and amount of data transmitted. The proposed strategy is to pursue this approach in a systematic way. If we draw a hypothetical platform of the emerging subsea technologies and knowledge, currently a bottom-up approach is followed to pursue their exploration. In fact, it could not be otherwise, because we have a fractioned industry supporting entities that manifest their requirement in a similarly dispersed way. This is what we can expect in the initial days of a new era. Process where the various entities cited execute their respective projects, different research, contract and collaboration tools are used. However, it deals with the knowledge platform in a way that creates overlaps and unattended areas. One of the consequences is that in the future we will not optimize interoperability. In addition, resources are not efficiently utilized and priorities are not easily identified. Instead, imagine that we can cooperate to define a top-down approach or apply the interface we presented above as a general criterion. So we should plan ahead for the implementation of the knowledge platform. This table has rows of technological elements encoded in a list. For example, launching systems, battery management systems, and communication systems. These solutions are connected to each other with standard interfaces that ensure compatibility. That is, each element has a default standard interface that communicates with adjacent elements. The columns represent specific projects, and these are defined as a selection of elements needed to complete each project. Each project requires that its black cells be completed. When a row is entirely or partially blacked out, this means that a technological element is completed, and any completed research can serve more than one column and therefore benefit more than one project. This optimizes the effectiveness of our actions, taking into account the limited resources we have at our disposal. For example, in the field of subsea communication, an optical system based on light coders can be useful in many projects. If everyone interfaces with the same data input and receiving system, the system is automatically compatible. This model could enable the Defence Administration or large corporations to make more effective use of small and medium enterprises, with significantly lower management and coordination expenses for both parties. What are the prospects? IAD is developing a database to map the technological capabilities of SMEs in the defence sector, which could be complementary to this vision. And pre-established defence programmes are funding new investments in the subsea defence sector. But we are also convinced that an effort to consolidate cooperation is needed by one and all within the industry. But in the face of global competition, the winning element continues to be coordinated teamwork between and within the Defence Administration and the subsea industry.